Today we talked about transforming functions, and this is brought to you by the absolute value function. So let's actually begin with this idea of if we had just f of x equals x, which is what this is, see, f of x equals x, what would g of x look like if it was negative x? So I think a lot of you know already that it looks like that, right? So what we're getting at is that we are reflecting, okay? So reflecting is when you are multiplying the output by -1, and that's going to flip the function. Now, if you were to say, hey, it flips the function, I'm going to assume that you are talking about reflecting. So it's okay if you want to use those words kind of interchangeably. And if you're like, well, what the heck, how is that thing flipped? It's flipped across the y-axis, right? Imagine you've taken this and you were able to somehow pick it up and turn it over. It would now look like that, right? So that is a flip, that is a reflection. The next thing we got going is translating vertically. Translating vertically. So again, we have f of x equals x, that's this, and that's what this looks like, right? But if you were to do this to that original function, if you were to take x, and then let's say plus 4, okay? Because see how they have a plus k? So, okay, I'll do this as well. X plus k, and then k can be anything, right? So here's what it would look like. Basically, when you plug in x is 0, you would now get 4 instead of 0. So here we are, 1, 2, 3, 4. If you plug in 1, you get 5. There's 5. You plug in 2, you get 6. There's 6. So notice that the slope is still 1. It's still 1. It's still 1, just like that. So all we're going to do is now we have moved this line up 4, right, in comparison to that one. So if you are going to do that, you are adding or subtracting, and by the way, this is where subtracting would come in. You are adding or subtracting to the output, which moves the function up, down, changing both intercepts. So this is kind of like, in my opinion, a little bit of an afterthought, but it is definitely true. So if you're like, what do you mean by it changes the intercepts? Well, right here, the intercept was 0, 0. The parent function, that's the intercept. But now, check this out. Our intercept is 4. So x is 0, y is 4. And then also way down over here, here, let me make sure I did it accurately. Down, 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 down. So it should be right there. My graph is not perfect. Should be at -4, 0. And that makes sense, right? That if we move this thing up 4, that it should be going through that. So here, let me graph this a little bit better. So it would look like, yeah, so that's a way better looking one. Sorry for the shoddy graphing. Like that, yeah? Cool. And then one thing I want to point out is this right here, output. You might be thinking, okay, well, I'm not really sure what he means by, you multiply the output or you add or subtract to the output. Well, if you have f of x, that is your output. And you might be thinking, okay, well, that doesn't clear it up for me very much. Well, that is your y. Because what happens is you input x, right? So as you're looking at this, if you were changing the output, it would be like, say this, where you would have 3x, or even 3x plus 4. If you were to change the input of this, let me show you what that would look like. In fact, we're going to do it here in a second, so I'm kind of getting ahead of myself a little bit, but let me show you what it looks like. We're going to erase, if it'll let me erase, we're going to erase the x. Because now instead of it just being x, what if I did x plus 1? Well, check it out. Then this would now be x plus 1. And I have officially changed the input, right? If this is my input, there it is there. Now I've changed it. Now I've changed it. So what was the point of telling you all that? Just to clear up, what were we talking about when we are multiplying or adding or subtracting to the input? I'm sorry, I just messed myself up. What are you doing when you multiply or add or subtract to the output? Is you are multiplying like the end result, right? Like this one, 3x plus 4. You're multiplying technically the end result. So let's jump in here. Translating horizontally. So notice it's like I just did in that little example, is that it's inside that little function box, or function parentheses, right? Notice how this is just regular old x, and this is definitely more than regular old x, right? So here's regular f of x again. And if we were to do f of x, let's just do, you know what? Let's do minus 3. So here's what it would look like. X g of x, okay? So this is where, I mean, it is going to look a little complicated because to do that, our g of x is made up of f of x minus 3. So what we're doing is if I plug in 0, I'm plugging it in here because this is what's inside g of x, okay? So if I plug in 0, then I get 0 minus 3, which is negative 3, okay? So when x is 0, y is negative 3. When x is 1, so that 1 is going to go up here. 1 minus negative 3 equals negative 2. So when x is 1, y is negative 2. When x is 2, well, I mean, we can even follow the slope. 2 minus 3 is negative 1. So when x is 2, negative 1. When x is 3, we're going to get 0. 3, 0. 4, 1. I think you get the idea. So here's the graph. Let me do the straight line instead of kind of doing the bad-looking graph. I think it looks like that, okay? So you might think, okay, well, you didn't move it horizontally. You didn't move it negative 3. I did. When it's inside of those parentheses, usually, and so maybe I just kind of screwed up by doing the minus 3, but usually what happens is we actually write this like g of like f of x minus h. And if that's like, oh, that's really weird, think of back to like point slope. Oh, okay, why is my writing so giant? Think of like point slope, where we had like y minus y1 equals m times x minus x1. These were negative to begin with. So that's kind of what happened here is that's negative to begin with. So it would move over to 3. And if you're like, I'm really lost, why don't I do one more? So what if we did g of f of x plus 4? So if I'm doing plus 4 to f of x, let's do a new table. So in fact, I'm going to erase this table. Bye-bye table. We're going to construct a new table. Okay? Right. So new table, x and g of x. But hold up, g of x is really f of x plus 4, right? Okay, so if we plug in 0, 0 goes right there. When x is 0, we have 0 plus 4, which is 4. And if you're like, wait, why is this 0 then? Because remember, f of x is really just x, right? F of x is really just x. Okay. So now let's plug in, let's say, oh here, let's go ahead and graph it. X is 0, y is 4. There we go. X is 1, we take the 1, we plug it in here, which trickles down to here. which eventually trickles down into here. So it's 1 plus 4, which is 5. So when x is 1, y is 5. When x is 2, again, we can use the slope, so it's 2, 6, 3, 7. And if you're like, why is it 7? Again, because it's 3 plus 4. So check this out. Here's my line, just like that. Yeah. So hang on a second. I said we were moving it positive 4, didn't I? And yet, where is that? That's negative 4. And again, if you're like, wait, why? I don't really get it. It's because it should technically be right here. This should be like f of x minus like that. So anyway, that is translating horizontally, where you can add or subtract to the input. It's the first time we're changing the input. We will move left or right, and it will change the intercepts. Why is this here? Because this was technically up here, just adding, and I changed it to adding or subtracting because you can add or subtract to do that. Okay, okay. Next, stretching and compressing. Okay, we are going to be compressing first, but we're going to start with, hey, listen, we just have f of x equals x. There's the regular guy. There's the regular guy, right? Okay, great. If you're going to compress, you are going to multiply the output or the input. And that's going to stretch the function. And it's going to stretch the function how? It's going to stretch it closer to the y-axis when a is greater than 1. And it's going to compress it when closer to the x-axis when x is between 0 and 1. And then if you're like, what? I don't really know what you're talking about. Basically, but if it's between 0 and 1, it's basically a fraction. Okay, so let's take a look at this, shall we? So f of x was just regular x. G of x is a times x, okay? And like we just said, you could either multiply the output or the input. So this guy right here is multiplying the input. In fact, why don't we zoom in and say that? Let's label it. This guy is multiplying the input. This guy is multiplying the output. How do I know that? It's not just because he's on the outside. It's because f of x, remember, y is our output, okay? And then a on the inside, that is our input. Okay. So zipping over here, if we happen to have 3x, so what that's going to be is there's our origin, there's our 0, 0, because we haven't moved it up or down or left or right. And all that's going to happen now is our slope is 3. So up 3 over 1, up 3 over 1, up 3 over 1, right? Like that. Now let's graph it. Just like that. Now, normally it looks like this. This guy looks like this. He has been stretched. Stretchity stretchers, and that's what we just did. When a is greater than 1, you're stretching. A is greater than 1. And what is our a here? Our a was 3. So we just stretched that thing. Now let's do a compression. In class today, I came up with something that I had never really thought of before because I mix these guys up all the time. But no longer, I think, because when you multiply the input or the output by 0 to 1, that is a compression, okay? And it's going to make it closer to the that's going to be closer to the x-axis. Yeah, see here it is, closer to the x-axis. Sorry, my eye caught that and thought that that was the right one. If you're compressing, you're closer to the x-axis. When you were, slide back down here, when you were stretching, it's closer to the y-axis. Okay, So maybe you got that really well and I'm just sitting here spinning my wheels, but I'm looking at this going, okay, so compressing is closer to the x-axis. So here's what I came up with today. Compressing is like compression. I know that seems stupid, but if you were to pronounce this compression or compression, there's an X in it. And now I know I should be closer to the X-axis, right? So if we had 1/3 X here, well, there's our origin. And if you're like, what do you mean our origin? Well, normally we're here at, there's the regular y equals x, right? Or f of x equals x. But now we're going to be 1/3 of that. So here's what you do. Basically, your slope is rise 1, run 3, rise 1, run 3, okay? And now let's graph it with a good-looking line like this. I think we did it. Okay. That thing is closer to the x-axis. It's closer than this one, right? So we have compressed it, or as I just kind of came up with a stupid little thing, we've compressed it, okay? Why compress? Because it has an x, and we are now closer to the x-axis than we were. And by the way, this is the opposite of stretching, okay? Now, this is some new information for us as of today because it's the absolute value. And this is a new parent function. Yay. So if your brain is full from those notes, why don't you take a break? I'm going to hit pause so you can take a break. Okay, here comes part 2. So we're looking at a new parent function. That's what it looks like. And people in class kind of pointed some things out right away. They're like, so does that mean we're going to have y equals x and y equals negative x? Like, is it going to be one or the other? And the answer is, it's both. Isn't that exciting? Because if you were to plug in 0, you get 0, duh. If you were to plug in -1, you get 1. If you were to plug in 1, you get 1. If you were to plug in 2, you get 2. If you were to plug in -2, you get 2. And if you're like, wait, why do you get 2? Well, because the absolute value of -2 is 2. So this is what you end up getting. Let's plot those points. 0, 0, 1, 1, 2, 2. -1, 1, -2, 2. Oh, look, it looks like that. So if we were to continue that pattern, it's going to look like that. It's going to look like that. This is our new parent function. It's like a V shape, right? Take a moment for that to sink in. That's the absolute value of x. That's y equals the absolute value of x. So let's run through some education about this domain, about this function. The domain is all real numbers. You could also say it's -infinity to infinity because, listen, you could hit x anywhere along this graph. Now, your range is definitely different because the range doesn't exist down here, right? Not for this one. So the range for this one is going to be from 0 to infinity, or you could say it as y is greater than or equal to 0, right? Is it continuous? Yep. And what's the difference? There's discrete, which would be just dots. This is continuous in that it's lines, right? Right. The x-intercept and y-intercept here are the origin. So 0, 0 for both of those. The end behavior, well, as x approaches infinity, looks like y is approaching infinity, right? And then the same thing on the other side. As x is approaching infinity, the y, or the f of x, is approaching infinity for both. So as we're going this way, looks like it's going up forever, right? Right. So I'm pretty sure if I just left you alone, you could have figured out these by yourself, right? And you still probably could. The graph is V-shaped. And again, you probably could have figured that out. But what about this thing? Well, that's kind of a new vocab word. The vertex is 0, 0. Now, is the vertex the same as the x-intercept or y-intercept? No. The vertex is this guy, where it goes from going down to going up, right? that's the vertex. You could call it like the corner if you wanted to. There's also some new vocab with axis of symmetry. Well, if you're like, symmetry seems familiar, yeah, here's the axis of symmetry right here. In fact, I should make that a little darker, a little fatter. There we go. There's the axis of symmetry. The axis of symmetry for this one is x equals 0, okay? X equals 0. It is always going to share the x of the vertex, okay? And then now, so okay, buckle up. That was all like the basic info. So now, you know how like we just spent all this time talking about how could you transform regular old x? Well, we're now going to jump into how can you transform f of x. I'm sorry, absolute value of x. So it's this. And if you're like, well, that seems scary, lots of letters. Yeah, it is lots of letters, but let's break it down into what we just did with all that other stuff. If you had the absolute value of x and you multiplied it by a number out front, okay, well, that is either going to stretch or compress it, right? If you were to, hang on, let's erase this little line right here. I'm just going to scooch it over for the time being. If you were to add to the output, well, that is going to be a vertical shift, a vertical movement, whatever you want to call it. And then if you were to add or subtract to the input, this is going to be a horizontal shift, okay? And if you could do all three of those at once, right? I'm pretty sure you, being the brilliant people you are, you could not only just move it over to the right, right? Like you could do that. That's not that bad. This would be here. So let's just do that real quick. Why don't we graph one? If we moved it to the right like that, and we moved it 3, right? So 1, 2, 3 right here. If we did that, this function is now y equals the absolute value of x minus 3. And if you're like, wait, how is it minus 3? Because that's definitely a plus 3 right there. Just like I was saying earlier with our horizontal shift, it's usually written with x minus h. So if you were to plug in a 3 here, a positive 3, then this would still appear as negative 3, right? And it does right there. And then if we were to move it up, let's say 5, so there would be our vertex. And I'm just moving it up, not doing both right now. Kind of just going one at a time with these examples. So if we move it up 5, the slope, the slope is not changing, so we're still going up 1 over 1, right? We're still going up 1 over 1, right? Like that. This equation is f of x, or y, equals the absolute value of x, then plus 5, okay? Because on the outside, it kind of keeps the same. So that plus k, if we put in a positive 5, it will stay plus 5. If we put in a negative 5, well, then it would be down here, right? And then now, let's do some combinations. So for example, we haven't reflected this thing yet. Let's reflect it. What if we had y equals negative absolute value of x? Well, imagine then taking this table, and when you plug in negative 2, well, you actually get negative 2. Okay, so here, I'm going to construct this table over here now, but keep an eye on the right side of your screen because we're basically going to be doing this. So I'm going to do negative absolute value of x. So when we plug in 0, we still get 0 because there's no such thing as negative 0. So there's 0, 0. When we plug in 1, okay, well, you would take the absolute value of 1, and then it would be negative. So we get negative 1. You plug in 2, you get the absolute value of 2, which is 2, and then it would be negative 2. So let's graph this. 1, negative 1, 2, negative 2. Uh-oh. Do you see what's happening? It's now going down, right? So that's that part of it. What if we put in negative 1 then? Well, the absolute value of negative 1 is 1, and then it's negative. Why is it then negative? Because of our negative on the outside, right? And we do -2, we get -2. Oh my gosh, so -2, I'm sorry, -1, -1, -2, -2, like that. And it graphs like that, okay? So check it out. We reflected it over the x-axis. So if you're like, why is he saying it like that? Because this is the axis we just flipped it over. And if you're thinking, again, I still don't know why he's saying it like that. Because earlier we flipped this graph. Our reflection was over the y-axis, okay? The y-axis, right? Reflecting, flipping over the y-axis. This one, flipping over the x-axis. Cool? Cool. Bonus info for you is, okay, I guess I should technically kind of finish this off. So remember I said that you could, find my right color, stretch or compress. So stretching is going to be the same. When your A is greater than 1, it's going to stretch towards the y-axis. So maybe I'll even write that underneath this. Towards y. And when you compress it, you're towards x. And remember, that's when this is a fraction, basically, right? When it's from 0 to 1. And then when it's -1, well, I kind of just spoiled that up there. It's reflected, right? So, sorry for the spoiler. What I was going to say is that this is kind of our first dive into what we call a piecewise function, because it's in two pieces, sort of, okay? And if you're like, what two pieces is he talking about? I'm talking about these pieces. This is on our graph, and so is this. This part is happening when x is greater than 0. I guess you could say greater than or equal to. And this one's happening when x is less than or equal to 0. And if you're like, what the heck does he mean? I mean, take a look at our line of symmetry. There's x equals 0. If you were to just look at this red line, that's y equals x. So that y equals x is happening on this side of the x-axis, meaning when x is, this side of the y-axis, which is when x is greater than 0. And this red line is y equals -x, and it's happening on the left side of the y-axis, which is when x is less than 0. So that was kind of bonus info for piecewise. I know I didn't graph two that are stretched or compressed. You know what? Why don't I just erase all that and do it? Okay, so let's see a compression or compression. So what if we did 1/4 absolute value of x? Well, there's our vertex. It's at 0, 0 because we didn't move left or right. We didn't move up or down, right? And this is kind of like our slope then. We're just going to go up 1/4, up 1/4. And then I'm going to do it in the other direction too, because that is how symmetry works. Since we didn't move it left or right, our symmetry has not changed. So then this is what a compression looks like. It's the absolute value. It's y equals 1/4 absolute value of x. That's what we just did. And then one more, we'll do a stretch. What if I did y equals, let's go with 6 absolute value of x. Okay, well, again, our vertex is here at 0, 0. And all we're going to do is basically go up 6/1. And I kind of made that tough on myself because I need to go off the graph for my next one, whatever. And then we just do symmetry. So there's symmetry. Let's graph this thing up 6/1, up 6/1. So what was the purpose in doing this? Remember, this is a stretch. It gets closer to y. And this is a compression closer to x. And then we already did one that was negative. But you know what? Now let's do one where we throw everything at it. We do all the things. So what if I did f of x equals, I'm going to zoom in because I don't know why my pen gets huge like this sometimes, but whatever. What if I did negative 2/3 x plus 4 minus 5? Okay, so this is going to flip and compress. This is going to move left 4, and if you're thinking left, isn't left negative? It sure is. Because remember, this is x minus h. And then this is plus k, so this is going to move up, down 5. Because why down? Because this is normally plus k, and if we have a minus 5, it must be because k is negative. Okay, so we've thrown a bunch of stuff at it. Let's see if we can figure it out. Well, first thing, our vertex is now -4, -5. So over 4, down 5, right there, yeah? And really, from there, it's just kind of the slope, right? So we're going to go down 2 over 3, down 2 over 3, down 2 over 3, down 2 over 3, and we just graph it from there. Like that, and like that. There we go. So, might seem a little funky, but we just graphed that, and it wasn't that bad. You just have to be able to decipher, or whatever, however you want to word that, what these three things mean when compared to just plain Jane abs of I of x, okay? So that was just the 2 pages of notes. I'm going to do another video where I obviously go through the assignment, but I wanted to make sure that you kind of knew what the heck was going on. Let me know what questions you have about these notes. See ya.